So we continue further on the lecture that we are doing on transfer printing. Here we will see the mechanism of transfer, and because it is just like a gas when you work in this transfer, so there is the concept of free path length. How much path is available before a molecule of a dye which is in a vapor form goes and strikes another one. So when you strike, things happen differently. So that's what something which will work around. In the case of the dispersed dyes as such, when we dye or print, we are looking at the possibility of some of the dye dissolving in whatever little water that you have. Then it goes into molecular form, and then goes to the surface, and then diffuses. In this case, we are expecting there is no solution, there is only air and a vapor. So it will vaporize, and the molecules will be in the vapor form, and then they have to traverse a path and go to the fiber. So this is what we hopefully be able to explain, and that's the way we can look at the mechanism of transfer. So stepping back, we understood that there is a requirement of ink. It would have some solvent which is relevant to the technology. There may be a binder which will be relevant for fixing, and also various types of dyes can be used for transfer printing, dispersed of course, and various other fibers, nylon, acrylic, cotton also could be transfer printed via sublimation printing. So at the moment we are still on sublimation transfer printing and not on any other transfer. So we go to the mechanism of transfer. So we know the dispersed dye polyester isotherm it follows solid solution. This should be valid here as well. It does not matter whether the dye is going through a solution or going from vapor form. Instead of solution, we will be talking about dye in the surrounding environment. So what we are expecting is the dye is going to vaporize from paper, not just paper, but we expect the dye is only on a layer of ink. It is not inside the paper, it is outside, but it is in solid form. After we heat, it is going to go into the vapor form. So instead of you talking about, let us say, dye in solution, you may say dye available in vapor form, the concentration of a dye in the vapor. That will become important, and dye on fiber of course. So there will be an equilibrium established, and this would of course change because the concentration of a dye in a vapor can change. And how will it change? It can change because of temperature. So it does not mean that if something is subliming at 190 degrees centigrade will not sublime at 200, but two temperatures are different. The receptibility of the fabric and fiber also is different, and the vapor pressure at a different temperature is also different. So the moment you come to gas, now you are looking at vapor pressure. Higher vapor pressure means obviously there is a molecules have higher kinetic energy, and they would be going from one end to the other end and trying to strike something. And so if they strike early, obviously they are on the surface. Once they are on the surface, affinity forces will start working, and because temperature of the fabric also is high, then diffusion will start taking place. So, conditions where the polyester fiber then convert to dye vapor, right. The distribution of dye at equilibrium is again governed by the same partition isotherm, in which the coefficient could be defined in the same manner, where the concentration Cf is the concentration on the fiber and Cv is the concentration of the dye in the vapor phase. We are not talking about how much dye was present in the ink on the paper. It is very difficult to find a correlation there. So, we are only interested in the dye which is in the vapor form. So, all we have to do is ensure that there is enough concentration of the dye in the vapor. Just before we have learned that the amount of dye which is actually going to be on the vapor, in the vapor, would depend on its molecular weight, right. It was dependent on solubility of the dye in the case of aqueous system. Here it is dependent on how much is the concentration in the vapor, and this obviously has something to do with the sublimation transfer, sublimation, which means the molecule, the structure of the molecule, and therefore is a complex process. And this is, as you have seen, a small change in intra and intermolecular hydrogen bonding can produce a large change as far as the concentrations are going to be there. And therefore, you definitely will be much more careful when you select a dye, mix the two dye together or three dyes together, or different colors which you choose from different parts of the design should have similar transfer rates. So, ideal gas, okay. So, nothing is ideal in this world, but assuming that it has an ideal behavior, then the concentration of a dye would be related to P, which is the vapor pressure, saturation vapor pressure. M is the molecular mass of the dye. So, if the concentration is in moles, it is a different story, and Rn is the gas constant and T is the temperature. If suppose somebody gives you a numerical problem, the only thing you have to understand is that the units must be compatible. Numbers always look compatible, right. But if the units are not, then you will get order differences in the results, right. So, whenever you have to solve any numerical, you should be concerned about what units are we talking about. So, simple relationship, the concentration of the dye in the vapor form will be related to the partial pressure or the saturation vapor pressure, that obviously you know indirectly dependent on the rate at which this can be evaporated, sublimation rate. The molecular mass, it is a gas, therefore, R and T are becoming important. The T, remember, is going to be an absolute temperature and not degrees centigrade, right. All right. So, before we go further, let us look at this. So, let us say this is a molecule of a dye being represented by some size. So, you have a size of a molecule, and this molecule is now in the vapor form and is rushing everywhere. So, the probability that anything which comes in its path, it will contact. So, it is not going to contact only the fiber. Fiber is much far off. When it starts in the vapor form from the surface of the ink layer, fiber is very far off. In between, there are a lot of molecules of the dye itself. It can sort of, this is a simplistic view, simplistic in the sense that all the molecules which are in the vapor of the same size, they represent spherical, and so they move as a particle from one to the other, or the molecule, and it can strike. And what will strike? If the distance it can strike, if the diameter of this particle, let us say, is d, then it can traverse a kind of a path which is a 2D, let us say a cylinder moving, and then the molecule goes from this side, can strike here, can strike there. If other particle is within the thing, how many particles are there within this range? So, the area of this particular thing is, if you consider pi d square, right, d becomes the radius of the larger pipe, shall we say this is a pipe, theoretical pipe. So, if it is in the center, the molecule will be here, but it does not have to be always in the center, it can be anywhere. So, this molecule is the same or something similar molecule. If the distance of this is more than 2d, then this particle may be here, it may pass through without touching. So, it may not strike. If the distance is like this, therefore, it is bound to touch, whether it is here, it is there. So, this is the thing that they say, let us theoretically say what will happen if this is the pipe where this is moving. So, within the 2D range, definitely anything that comes, it will strike. We are assuming that all the particles, because of our Newton's law, will move in straight line till they strike something else. When they strike, they can change. So, they have a velocity and a direction, obviously, they are moving in particular direction, and this direction need not be in one direction, they can go in anywhere because they are free. The movement of particle or a molecule is out of the particle, vaporized, then is free. The kinetic energy does not say you go only in x direction, y direction, unless and until you create such situations, you create a vacuum on one side, then they would obviously get tendency to go in one direction, but forget about that. So, it is going to move. When it moves from one end to the other end, it will keep on coming in contact with particles, and once the interaction is there. So, what people would like to know is how much is the free path likely to be there where it just moves without hindrance. It is not possible theoretically, but if suppose the path length is just that starts from the ink and reaches the fiber surface and no one has come in between, it is not happening because molecule is too small. You understand Avogadro's number? So, think about those numbers, very small molecules, so many of them all over the place, and therefore, you talk about concentration buildup. So, as we said, the area assumed virtual pipe in which there may be so many molecules, and they would go from one end to another end, let us say, of the pipe. In between, they would probably connect with many other molecules also. So, the time taken, all right. So, mean free path could be expressed as the distance traversed divided by the number of such collisions. That would also mean that there have to be how many molecules per unit volume, something like that is available. So, the volume of this virtual cylinder can be pi d square. V bar is an average velocity which is travelling. Average means we are not hoping, or we are hoping that some particle or some molecule from one end has reached the other end, and some of them could actually go absolutely out also, right. So, whatever we are looking at, some those who pass through in one direction, whichever the direction, and went around. So, in this virtual so called cylindrical path, you would have the volume is there, and so if NV, which is the number of molecules within that so called unit volume, then the lambda is therefore distance divided by the number of possible collisions, and which means this is 1 by pi d square I am sorry, I have used D sometimes capital. Let me just make all of them small. Maybe it's not working, so let me just make this is small d and this is also small d, okay, right. So pi d square, average velocity v bar and number of molecules are the ones which are going to decide that the lambda will be, therefore, if we write it again, is 1 over pi d square and n v. Is that okay? So, it is dependent on the size of the molecule and dependent on the number of molecules. The problem is that the average molecular velocity is being used in this expression, but it is not that the molecule which is going to strike are stationary, they are also moving. None of the molecules is just stationary, it has a velocity in whichever direction is going, it can still strike, and therefore, the collision will depend on the average relative velocity of randomly moving molecules and not just an average velocity, but average relative velocity. So, you have to find a relative velocity. So, how do we find the average relative velocity and what do we mean by that? That one is moving with a v1 velocity, the direction also is seen, it is one single particle. So, is the direction of the, it is a vector quantity. So, you are showing as a vector v1, other is moving with the vector velocity v2, but when they vary around one way or the other, let us say one is moving in this, the relative velocity therefore would be v1 minus v2, all right, and so, and there will be so many relative velocities also. You strike and go somewhere else and all those kind of things. So, you work about average relative velocity. How do we calculate that? So, a relative velocity is like a dot product of the differences of one and the other, square of that, then multiply and then take the square root. And if you do that, you get terms like this, because all of them are also moving. So, all these terms will also can be averaged out. So, this shows that the average velocity will be v velocity, which is a vector v2 vector, then minus 2 v1 vector, v2 vector and v2 and v2 vectors, and then square root of that. Now, that becomes mean average. Now, what we get is the average velocity will not have this term which will be equal to 0, because they are moving randomly and their products on an average everywhere, if you look at it, they will become 0. One moving this, the other moving that, something moving this, but v1 square obviously will be there and v2 square will be there, then average of those products, and then you take the square root, and therefore, relative velocity is not just v average, but root 2 of v average, and that becomes a change, and that if you make that change for a single molecule, that is in the whole thing there is a single molecule, then you can use this term rather than the other term, and therefore, the lambda, which is the mean free path, would be 1 over root 2 pi d square and the number of molecules in that unit volume. Okay. And if we again say that n can be the number, the moles, and plus Avogadro's number. Na is Avogadro's number, and then the whole number Nv can be expressed as capital Na, which is the Avogadro's number, the pressure, which is the saturated vapor pressure, R and T. And so, the free path length will also depend on the temperature, it depends on the pressure, right. So, if pressure is high, path length will be less, and dependent on the D, of course. So, this is how one can roughly say, well, this is the way I can consider this will be the path length. Interesting. So, let us assume that all the ink is on the paper. So, paper also has some thickness. Then now what is there is, let us say this is called ink layer. Then there may be some gap, which is the air gap, and then there is a fabric on the other side, which is the fabric. Now, if you assume this, interesting way to look at it is that you consider this as the axis which is representing concentration. So, at a given time t is equal to 0, all the dye is here in the ink layer. So, maximum concentration is there. The concentration of a dye in the fiber is 0. So, there is a gap, there is a distance, and we hope that in the paper layer, whichever, there is no dye concentration. So, this is what is there. So, we have ink on the paper layer is followed by the ink layer, then there is a air gap followed by fabric of a certain thickness. Okay. So, this is what we expect to happen. This is the situation. What will happen is, with time, when you apply heat, then some vapor formation will be there, and once the vapor formation takes place, then the concentration of the ink in the ink layer will go down, okay, and in the others it will start increasing. Okay. Let us say we work. Same situation, paper thickness remains same, the thickness remains same, but the concentration of ink, let us say, goes down at, say, time t is equal to some time t1. It will go down, concentrations go down. So, this is, remember, we are talking about concentration on this side. So, where will the dye go? This is the fiber and that is the gap. So, dye will come on this side. If we measure, let us say this is the distance, molecule has to cover a distance. So, we say maybe this concentration profile is something like this, that there is a dye which comes out in the air, but near the ink layer the concentration is more, near the fabric surface the concentration may be less, but by the time if we look at for whatever thing some dye has come into the fiber also. So, at T is equal to T0, dye concentration is maximum in the ink, right, that is what to say, is maximum in the ink. The dye concentration is maximum in the ink and no dye was in the gap or in the fiber. At T is equal to T1 and the temperature rises, some dye has vaporized, has come to the air gap, some of the dye has diffused in the fiber, the concentration being more on the surface and reducing as one would traverse to the core of the fiber. So, this is what we said, that the concentration will be more on the surface of the fiber. As you go inside the fiber, the concentration of dye will be less. Something similar is here. When we go to a time, again the paper and the ink layer, if everything is nice, good amount of dye may have gone, the concentration in the ink layer would go down. In the air there may be some concentration, but at an equilibrium. On the fiber we hope that the concentration not only has risen, but is probably uniformly distributed when at time is equal to infinity. That is the equilibrium. Possibly some dye may diffuse also in the paper, all right. So, you have very less amount of ink remaining on the ink layer, it cannot be 0 in the vapor, but most of the dye may have reached where it was supposed to reach, and this is how one can describe. So, at T is equal to infinity, what happens? At T is equal to infinity based on the partition coefficient. Now, this is here all that affinity forces would be working, the molecule, molecular size, the temperature will working. We hope that dye would diffuse uniformly in the fabric at the as the equilibrium is achieved, and very less dye vapors in the air gap, and some may also diffuse into the paper as well, right. So, this is a general way of describing the same thing which we tried to describe in a solution and the fiber surface. So, the gap is important. How do we alter the gap? Well, we apply pressure. If we apply more and more pressure, the gap will be less. That means the chances of this transfer to the fabric will be quicker, and other diffusions here and there also will be less, and so it will be in our own interest to reduce the gap, because the gap would mean there is air, it is not a vacuum. The molecule is not travelling through the vacuum. If there is air, there are other molecules also. Then the whole equation becomes very complex. A large molecule and a small molecule hitting each other, what is happening and things like that. So, any air particle is a additional resistance to motion. So, it is not just distance to be travelled, but you will be encountering many other kind of particles, molecules, which will also hinder the motion. So, gap reduction means pressure. Some examples before we close. You see, I've just taken some example where the molecular weight is similar and where the molecular weight is different. So, the die manufacturers are defining these pressures etc., at a temperature 200 degrees centigrade, right. So, they say, well, this is the thing, sublimation will take place, most of the people will be using. So, all the properties will be available measured at this temperature at 200 degrees centigrade. So, what do we see? We see that there is something dispersed blue with 266 as a molecular weight. At this temperature, it has got some vapor pressure, and based on whatever thing we have, the amount, the concentration of this is somewhere around 10 raised to minus 4. Remember, we were talking about concentrations of grams per liter and so on and so forth. And now we are talking about very less concentrations, but it still works. At 350 molecular weight of one of the other die, which is blue 56, the vapor pressure is very low and the concentration expected is 10 raised to minus 5. And when you have another die which is 242, vapor pressure is 21 and the concentrations are in the range 10 raised to minus 3, right, of in a liter. So, we are obviously looking at very less amount of molecules because they are really molecules and not particles, and they are ready to go wherever they want to go. But the difference is quite large, minus 3 to minus 4 to minus 5. And this is where one should appreciate that unless and until you choose your dyes correctly, then you will be getting whatever you see on a paper, what you see on fabric will be very different. The shade will be changed if this is the kind of order. So, this order is quite a lot of difference order, and one can always say why this is happening. Well, this is again the molecular structures that you have, the oxychromes that you have fixed up, the hydrogen bonding that they make, etc., etc. I think with this, as far as today is concerned, we can stop. So, we have understood what is a mean free path of a, at least for a single molecule moving around in an ideal gas environment, and the mechanism of transfer of the dye from the vapor form to the fabric. Thank you.